Correlation between x and y equals what? First year කරනවා දරුවනේ. Correlation between x and y. I'm sorry, sometimes I say things in Sinhala. I know there are few students who might not understand. Sorry about that. I'll try to minimize that as much as possible. Covariance between x and y. You can write with those equations, summation xi, xj, not like that. Simply saying using variances and covariances because you have a covariance matrix. Yes, Tarushi, correct. Correlation between x and y. Don't remember. Anyway, so it's the covariance between x and y divided by square root of variance of x, variance of y. That's how we find the correlation between two responses. Now, in a variance covariance matrix, you have the variances for each response and you have the covariance between the two. So you can easily calculate the correlation coefficient. So I'm asking for the first matrix, what are the three values? R1 to determinant S and trace of S. I'm pretty sure that determinant and trace you can find easily. Correlation. I already gave you the formula. Covariance between square root of variance x and variance y. Yes, Tarushi, correct. Yes, Hashini, correct. Dasita, yeah. You both are saying R12. That's correct. Ashoka, three values. Yes, all three correct. Yes, Tilshan, correct. Pavanti, correlation. Other two correct. Yes, correct. I thought that you have made probably a small mistake. There are 34 students. Nadine, where are you? Nirasha, Ushan. Some are just numbers. I don't know who they are. Ukshala, Tansni, Chatuni. Kalpani, I don't think I saw your name at all in answers. Nimni, Nimasha, Anjana, Anjula. Tarit. I'm just reading the names that are not familiar for me. I mean, I haven't seen any answers. Probably today. Sapchit, I think you gave one answer. Sasangi, yes, you did. Tula. Yes, get mini, Rukshala. Rukshala just R12. Other two. Yes, Nimasha. Yes, Shashika. No, Shashika. Correlation value, just check. And also determinant. Maybe it's for some of you. R12. I'm going to calculate R12. Covariance between the two is 4. Variance of x 5. Variance of y also 5. So 4 over 5.8. Sometimes you make careless mistakes. I just say things here, don't care. I'm just saying. At least incorrect answers, I really like to have something here in the chat box at least. Yes, Nirasha, yes, Chatuni. Determinant, just AD minus BC. 5 times 5 minus 4 times 4. 9. Right. Trace of the matrix, 5 plus 5, 10. Okay, now second one. Correlation, determinant, trace. Answers, please. Yes, Tarushi. Yes, Ashoka. It's okay, just take a minute or two. Nimni, correlation is correct. Please check the other two. You have done the harder part correctly. Pashan is correct. Yes, Pavanti. Yes, Chatuni. Yes, Sasangi. Yes, Nirasha. Yes, Latmini. Is this Samadhi? Yes, correct. Nimasha, correct. Yes, Rukshala. I hope that time is enough now. R12, yes, minus 4. That's the covariance divided by 2 variances. Again, 5 times 5. It's negative 0.8. Determinant, 5 times 5 minus 4 times minus 4. Same thing, right? 9. Trace also. 5 plus 5, 10. Correlation, determinant, trace. For S3, what are the values? Yes, Tarushi. Yes, Nimni. Yes, Hashini. Yes, Nimni, good. That's correct. Sasangi. Tunay එකතු කළාම කීයද දරුවෝ? Pavanti correct. Chatuni correct. Rukshala is correct. Yes, Kalpani. Probably that's a careless mistake. Don't worry, but yeah, try to minimize your careless mistakes too, right? Yes, Ishan correct. Nadeem correct. Get Mini, yes. Nimasha, yes. Right? Yes. Tasneem, yes, correct. Now 32 students. Man nam කියනකොට කට්ටිය අයින් වෙනවද දන්නේ? Don't worry too much, right? I try to make all of you participate in the class. Yes, as I always say, right? I like if you learn something. Yes, Samadhi, correct. Okay, yeah, the correlation obviously 0 because the covariance 0. So correlation 0, determinant 9, trace 6, right? So these are the value. Now recall that what we were trying to say here, right? So we use the example to say that if we summarize our data using the correlation matrix, if the number of distinct values are larger, we go for further summary measures called total variance and generalized variance, right? That's the theory. So there are, if P is large, number of distinct elements in S would be larger. So we'd like to have a few number of summary measures. So we use two other summary measures derived from our S, which are the total variance and generalized variance. But this says, however, as the following example shows, there are instances in which these summary measures fail to detect important differences in correlation structure. So clearly, right, you can see when we look at the correlation structure of the data, first one, 0.8. How do we interpret a correlation coefficient? Usually there are two things you have to mention. You have to say whether it's positive or negative, whether you have to say it strong, moderate, or weak. So what's the interpretation of the correlation for the first one? If you have a correlation of 0.8, how do you interpret that? Yes, Dasita, correct. Others? Yes, Tarushi. Yes, I mean, Sushan. Yes, Pavanti. Yes, Rukshala. Yes, Nimni. Yes, right. It's a strong positive relationship. So we are considering bivariate cases. That means two responses. So first one, strong positive correlation. Second one, strong negative correlation. The third one, no correlation at all, right? Those are our three variance covariance matrices. But when you look at the generalized variance, you can see all three generalized variances are equal. And when you look at the total variance, first two, the total variances are the same. The third one, 6 little less, but still kind of like close values, right? So if you decide about the data, if you decide about the data, just using the total variance and generalized variance, because we prefer these summary measures derived from our S, but don't always try to make decisions based on just the total variance and generalized variance, right? Uh, you may miss really important correlation structures in your data, right? You can see three completely different correlation structures here. So every time you try to summarize your data, don't just depend on the total variance and generalized variance. Give the correlation matrix, look at the correlation matrix as well. Then you can see whether there are highly correlated responses there or not, right? So the final thing, we can use this total variance and generalized variance to summarize our data, but don't always rely just on them, right? Look at the correlation structure as well. Okay, so that's something you have to remember. Do not interpret the values just using total variance and generalized variance. Then noting that trace of S equals the sum of the eigenvalues. We know that already from the matrix algebra, right? Trace is the sum of the eigenvalues and the determinant is the product of the eigenvalues. It is perhaps useful to report the individual eigenvalues as well. Yeah, because if there's like 0 eigenvalue, you know that, right? It's a singular matrix. Likewise, there are important features. So it's good to report the eigenvalues of a matrix as well. Since it is easy to see the correlations directly from R, capital R stands for correlation matrix, it is advisable to report R together with the sample variances of individual responses rather than reporting the sample variance covariance matrix. Yeah, just sample variance covariance matrix, you cannot get an idea about the correlations at all, right? So it's always good to report the correlation matrix as well. And that would be helpful if you summarize the spread using total variance and generalized variance, right? So always when you comment about a data, spread of the data, you can use total variance and generalized variance, but always look at the correlation structure or correlation matrix as well, right? Okay, so that's the summary, summarization part, numerical summaries, mean and variance covariance matrix. Any questions so far? Any questions? No answer, so I assume no, right? Okay, then properties of X bar and S. X bar is the variance covariance, sorry, sample mean vector, and S is the variance covariance matrix. Now, let X1, X2 up to Xn be a random sample. Okay, now I'm asking, what's the dimension of each of these? X1, X2 up to Xn be a random sample from a joint distribution with, you don't need the rest of that. When we say a random sample from a multivariate distribution, our standard notations, right? We have our data are n by p matrix. So when I say X1, X2 be a random sample. So random sample means these are observations. X1 is the first observation. X2 is the second observation, right? Likewise. So what's the dimension of each? Yes, Tarushi, Rukshala, yes. In the matrix, we see it as 1 by P, but I said when we say observations, we always refer to P by 1 vectors, right? Yeah, thanks for answering both of them. Not incorrect, but remember when we say observations, we say P by 1, not 1 by P, right? Tarushi is correct. Those are P by 1 vectors. Remember that when we say multivariate observations, those are P by 1 vectors, because for each individual, there are n individuals. For each individual, P responses are measured, right? So there are P, what's it, my pen? Yeah. So in each observation, P measurements are taken. So each of these are P by 1 vectors. Remember that, right? Each of these are P by 1 vectors. Be a random sample from a joint distribution with mean vector mu and covariance matrix sigma. Then X bar is an unbiased estimate of mu and its covariance matrix is sigma over n. Unbiasedness. An estimator is unbiased if, how do we write? You have done inference, right? Estimation part is done. This semester, I think testing is going on. So X bar. Unbiased means Ex bar equals what? An estimator x bar is unbiased if x bar equals, yes, Ashok, mu, right? Yes, Tarushi. Ex bar equals mu. And its covariance matrix. That means covariance of x bar equals sigma over n. When I write, I usually cut off sigma when I refer to variance covariance matrix, right? Just to separate out from summation. But in the note, there's no way of cutting it off. So I have direct sigma here, right? So when I type, I always try to give the limits if it's a summation. So I don't think that there would be mix up. But anyway, when I write, I usually use this notation with line to say variance covariance matrix. Okay, it's a random sample. Now it's unbiased and covariance matrix sigma over n. Proof. Can you prove it? You have the same thing in univariate also. If you remember how to prove it, you would know. So in the univariate case, my pen doesn't write. Okay, fine. Okay. Okay, univariate. So if you have a random sample x1 up to xn, these are just single observations, right? In univariate case. So x bar is, 1 over n sum xi. I goes from 1 to n. So we prove that expected value of x bar equals mu. How do we prove? Exactly the same thing here in multivariate case. So we prove this using the same equation. X bar we plug in 1 over n summation xi. So we can take 1 over n out, and expectation we can put it inside the summation. I goes from 1 to. So it's 1 over n expected value of x1 up to expected value of xn. What's this expected value? Ex1 up to exn. What are the values? Ex1, it's the same value. All Ex1, Ex2 up to Exn, all of them. Yes, Ashan. You are not so sure. Using a question mark, that's fine. Yes, it's mu, right? We expect each observation to be mu. Yes, Tarushi, correct. Right? That's why we usually, I know that everybody knows that mean is unbiased, right? So if I ask, probably in inference class, this question was asked from you. What are the other unbiased estimates for mu? An unbiased estimate for mu is x bar for sure, right? You know that one. Any other unbiased estimates for mu? Yes, Ashoka. each observation is also unbiased for mu, right? If you are asked to give few unbiased estimates for mu, not just x bar, right? X bar is just one value. You can give any observation as an unbiased estimate for mu. So each of the observations we expect to be mu. So then it's easier n times mu, n cancel off and you end up with mu, right? Same thing here. You can follow the same thing. The only difference is x is each x is a vector, and also x bar is also a vector. So you have to find expected value of x bar, where x bar is 1 over n summation 1 to n xi. Each xi is also a vector, right? So same way, 1 over n you can take out, summation also you can take out, expected value of each xi. The only difference is x's are vectors here, p by 1 vectors, right? So it's the same thing, 1 over n. This one is n times mu vector. So n cancel off. Mu. So x bar is an unbiased estimate for mu. Then in univariate also we prove variance of x bar, right? So same thing, variance of 1 over n summation xi. So 1 over n take out from the variance, it becomes square, right? You know the things. Same thing here. Variance of x bar. Variance of 1 over n. Variance or covariance, either one. Sometimes we use variance, sometimes we use covariance, sometimes we use variance covariance matrix, right? When we write. So same thing, right? Variance or covariance or variance covariance matrix, it's the variance covariance matrix all the time, unless specified otherwise. Summation 1 to n xi. So 1 over n comes out as 1 over n square. Summation variance of xi. So variance of each xi, that's sigma, right? Sigma. So it's again, sorry, n square, n times sigma. 1 n cancel off, sigma over n. Right? So sigma over n is the variance, covariance matrix of x bar. It's similar to the univariate case, right? In univariate, this comes as sigma square over n. So here it's sigma square is the variance. So here sigma is the variance covariance matrix divided by n. So that's the variance covariance matrix of x bar. Any question here? And remember this thing, right? You have already learned this, but you may not remember. So when we say x1 up to xn is a random sample from, so we still didn't talk about normal. Yes, Anjula, that's fine. I'm going to stop in about 5 minutes. That's fine. You can watch the video later on. So if we say x1 up to xn is a random sample from some kind of distribution, we'll say normal, mu and sigma square. That means each of these has that one, right? Expected value of each x is mu, variance of each x sigma square, right? That's the meaning. So x1 up to xn is a random sample from this distribution, means each observation has that distribution. So each observation expected value mu, variance is sigma square, right? Same thing here in multivariate nature also. Okay, the second one. First one, this one actually you can prove even by yourselves. And second one, I did not expect you to prove by yourself because it's a bit positive, definite, and those things also we have to say. The second property, the sample covariance matrix S is symmetric and positive semi-definite, right? S is symmetric and positive semi-definite. So recall that S is this one, right? Remember the matrix form? 1 over n minus 1 x transpose hx, where h is I minus 1 over n 1 1 transpose, right? So you can show that S is symmetric and positive semi-definite. First, you have to show H is symmetric and idempotent. Can you do that? I have already given homework, otherwise I would have given this also as a homework. Right. So H symmetric. H is I minus 1 over n 1 1 transpose. If H is symmetric, S is definitely symmetric, right? Because S is 1 over n minus 1 x transpose hx. How do we show that a matrix is symmetric? What do we have to prove to say that a matrix is symmetric? Properties of transpose and all, we have already done the matrix algebra. If we want to show that A is symmetric, what's the property we have to show? Yes, Nadine, exactly. We have to show that the transpose equals the matrix, right? Then it's symmetric. So we just have to show that S transpose equals S. So if you take the transpose 1 over n minus 1 as it is, if you take the transpose of x transpose hx, it goes the other way, reverse order with transpose. So x becomes x transpose, h becomes h transpose, x transpose becomes x. So that's why we say if H is symmetric, definitely S is symmetric, right? Because if H transpose is H, then S transpose equals S. So that's why we want to show that H is symmetric. To show that H is symmetric, we have to show that again same thing. We have to show that H transpose equals H. H another. Now I'm asking all the properties. A minus B transpose equals what? Please try to answer these small questions. You will at least recall the things that you need. Because in multivariate analysis, we did the matrix algebra first. Because we have to use them. Yes. Whoever this number. Nimni. Yes, Nimni, correct. A minus B transpose equals what? Others? Yes, Nadine. Yes, Chatuni. Mataka නැත්ද කමන්නේ. When you use these things few days, you will remember this stuff. A transpose minus B transpose, right? Yes, Pawan. With the question mark, but yes, correct. A transpose minus B transpose. So I transpose is I, you know that. minus 1 over n 1 1 transpose 1 1 transpose transpose. Again, it's 1 1 transpose, right? So H transpose equals H. So H is symmetric. H symmetric means S transpose equals 1 over n minus 1 X transpose Hx. That is S, right? So we know that S is symmetric. Okay. Then to show that it's positive definite, we have to show that H is idempotent. To show that a matrix is idempotent, what do we have to show? To prove that a matrix is idempotent, what do we have to prove? To show that H is idempotent, we have to show, yes, Shashika, correct. You used A, that's fine. The matrix is idempotent if නිදිද මන්ද කට්ටිය පැය 3ක් යනකොට එපා වෙලාද? Yes, Tarushi. Yes, Ashok. Yes, Nadeem. Yeah, this is the only way that I can figure out that you are there listening to the lesson. Otherwise, how can I know? That's why I ask these small things. You may not remember, but it's good to remember this stuff, you know, when you do something. Yeah, the answers I got only 4, but all 4 are correct. If you show that H times H equals H, then H is idempotent, right? Yes, Nimasha. So, if possible, just try that out also. But yeah, next time I'll do that. H times H equals H. And yes, the second property I'll finish the proof next time. Right. Any questions so far? Any questions or comments or suggestions, whatever? If it's too boring, you can say like, we'll try to do something, giving more examples or something. Don't know like what I have to do because I cannot see the faces. You know, it's really hard to teach without seeing the faces because I don't know whether it's boring or you are sleeping. Because in a class, even though you sleep, we can see. Still you sleep, I know. But still we know that, okay, for him it's boring, something like that. But here, I don't know whether any of you are listening. Otherwise, you answer my questions or something, right? So I'm asking again, any questions so far? Or any suggestions or comments? So you can say if I'm too fast, you can say I usually speak fast. That's a problem. I know. I try usually to slow down, but I don't know whether it works all the time. But anyway, okay. Thanks, Nadi. So I hope it's clear for others also. So if you have any questions, yeah, just drop me a message or email some way. Just contact me, right? If you have anything, then I can consider. Okay, otherwise we'll stop. I know you have another lecture at 1. So yeah. Okay then, see you next time. We'll wind up the session. Do the homework and upload. Okay, have a good week. See you next time.
Thank you, madam.
You're welcome. You're welcome.
Thank you.
You are welcome.